I still think
they're also called absolute. They're also absolute.
a function need not have a minimum or maximum value to affect the existence of an extreme.
All that makes sense, right? So here's my summary. Listen up. I'm gonna make it short. All you need to know is when I say absolute minimum, that is another word for global minimum. So if I alternate those two words, whether it be on a quiz or test, don't be surprised. And then there's also something called the absolute maximum, which is also called the global maximum. And on the bottom, I'm going to reiterate it by a drawing. So here is our condition. The extreme value theorem, that I'm going to call it EVT from time to time, has a condition that the function must be continuous on a closed interval, not open interval. Then we know the function must have an absolute minimum and a maximum. So let's do a random example. And before I do, I'm going to reiterate the condition. The function must be continuous, meaning there must be no hole and no vertical asymptote. And it must be closed. I'm only reiterating the definition. And let's do a random example. And I'll give you two for a good reason. So how you draw this really in the end does not matter, but I want to include a cusp. Because cusp still means it is continuous. So at this point, given the graph, can you pinpoint out the highest point of the graph? Is my highest point up here or right here? Top left, top right, where? Right here. So this is called the absolute maximum. In another word, instead of absolute maximum, is global. Now, given this figure again, could we pinpoint out the lowest point of the graph? Yes, we can, right down here. That is called the absolute minimum. What's another word instead of the absolute minimum that I could use? Global. And to reiterate that we have a closed interval, let's go ahead and put a dot at the endpoints. And I know as long as it's not a clear open circle, it is understood to be a closed in, but why not? So I'm going to give you another example then. So we're assuming at this point that the absolute minimum and maximum should only happen in between but not at. So let's change this graph to something that looks like this. And to reiterate, closed interval, put your dots at the end, although it is not needed. And I think I want to go ahead and put dots at the extreme points. This could be extreme, that could be extreme. So I'm going to call this 1, 2, 3, and 4. So between 1, 2, 3, and 4, what is my absolute maximum? 3. So we have absolute maximum, which is also called another word of what? Global. So between 1, 2, 3, and 4, what is my absolute minimum?
4.
4. That's lower than 2. So here's our absolute minimum. And there's a reason behind this. Your absolute minimum or maximum can be the endpoint. All right? Just keep that in mind. It can be the endpoint. Because when I go to the next page, it cannot be the endpoint for the next vocabulary. Is everyone good on that? So now let's make our card. And for me, it's card number 4. For some of you guys, maybe it's card something else. I think I'm going to put something underneath it. And I'm naming it as 3.1a, called the extreme value theorem, EVT. Please write this down. Because having the little cards and looking over them is easier than going through a big packet. So our condition is, if the function is continuous on a closed interval a and b, with the graph given, and you can make any graph you want, or you can just kind of use the graph that I have on my card, and go ahead and write the example or draw the example. And when you're ready, let's go on to the next statement. Okay, 10 more seconds.
It says it must be.
Then there must be an absolute minimum and a maximum. I thought my handwriting was on point. No?
I didn't know what the absolute.
Is it you or is it me?
I didn't know it was ABS.
There you go. How's that?
Amazing.
Amazing. That's what I wanted to hear. My A's look like U's too. I'm going to go back to writing school over the Thanksgiving break.
It's okay. We know you have messed up. Like, anger, right?
You call me mess up now?
No, I'm just.
Okay. We're recording. That was Xavier, by the way. My thumb problems, right? Permanent. Yep. All right. Let's go on to. Have you seen the video where I had the braces last year?
Braces?
Like a thumb brace? No? Okay. I should just say you should have seen the other guy. But no, it's not. All right. Let's go on to the next piece. All right. Story time. Meet your neighbor. Go. Just that piece. I'm going to summarize it.
Sit by the fire. If there is an open interval between C on which f of C is the maximum and f of C is called a
Hudson, we're reading.
relative
We're reading.
There's an open interval containing C on which f of C is a minimum. F of C is called a relative or local minimum.
Did y'all read 1 and 2 already? Yes? So here's my summary. If there is a maximum on a graph, isn't it changing direction at the point and going downward? It initially goes up and then goes downward. And if there's a minimum, it is initially going down and then changes direction and goes up. Bottom line is, for this to happen, can a relative extrema happen on the endpoints? On the endpoints? Do we know how the graph is going to behave at the endpoint if that's all we know? No. So it's never the endpoint. No endpoints. Oh, that's not endpoints. Endpoints. It is never the endpoints. So specifically, the relative extrema, which is also called a local extrema, is where it changes directions, just like the picture that I just made right above. Xavier, write this down. Changes direction. Whoop. So let's look at our picture on or directly below. And let's put our dots at the extreme points. So I'm going to go ahead and name and ask 1, 2, 3, 4 again. Where's my absolute maximum? 1, 2, 3, 4, 4, absolute maximum. Where's my absolute minimum? 1. Where's my relative maximum? 2. And that is where it is changing direction. It's also called the local maximum. At what point is my relative minimum then? 3. And what's another word for relative? Local minimum. So these are by the visual, and I'm going to actually show you a proof by algebraically. So Alan, go ahead and read the instruction right above A.
Find the value of the derivative at the indicated relative extrema.
All right, let's go ahead and box derivative. The derivative is our prime, f prime of x. And before we actually do this, I want to kind of anticipate. At this point, can I make a horizontal tangent? Yep. When you have a horizontal line, and mine's kind of off a little bit, what is our slope in a horizontal line? Ooh. If you have a flat surface, is it going up or down at all? Must be 0. Now, you did not have to know that because that's the part I'm going to prove to you. That's just me anticipating the endpoint. So, let's start by rewriting this. Our f of x is equal to, I want to distribute the 9x squared minus 27 over the x cubed. Because I do not want to use quotient rule, I'm going to go ahead and make it into a polynomial. So we have f of x. If I take x squared over x cubed, isn't it bottom heavy by one more? But because I want to use power rule, I want to bring it up with a negative 1 power. Then we have minus 27. Again, it's bottom heavy by 3 more. Bring it up with a negative 3 power. So now it's easier for us to use or find the derivative. So here we go. What is the derivative of 9x to the negative 1?
Negative 9x to the negative 2.
There you go. Negative 9x to the negative 2. What is the derivative of negative 27x to the negative third? Positive something. Ooh. 81. Good job. X to the negative 4. And since I know I have to prove that the slope is 0, I want to go ahead and rewrite this so it's friendlier. Negative 9 over x squared plus 81 over x to the 4th. And at this point, what I can do is the following. What variable do I have right now? I have the x's. In my point given, what is my x? 3. Let's plug it in. So we get negative 9 over 3 all squared plus 81 over 3 all to the 4th. And that is going to give us negative 9 over 9 plus 81 over 81. Isn't that basically negative 1 plus 1? So what is my slope?
0.
So I pretty much proved it to you. So we were anticipating it because we knew a flat or a horizontal tangent is 0, but there's my proof to you. Okay? So let's do that with the trig function on part C. How many points are we wanting to test on this one? How many dots are given?
2.
2. So let's go ahead and write our anticipated horizontal tangent, and we know our slope is 0. You didn't have to know that at the beginning, but just know that is what we are going to get to in the end. Circle the x value. We are going to plug it in the end. And let's find f prime of x. What is the derivative of sine?
Negative.
Ooh, cosine of x. So when I plug it in, f prime of pi over 2 first. Cosine of pi over 2. So let's go over to the right side and make our quadrantal. Pi over 2 is 90 degrees. Put a dot on our unit circle. The order pair of this is 0, comma what? 1. Cosine is adjacent movement. Isn't the adjacent movement the x movement? So we know cosine of pi over 2 is 0, and I just proved my point. Let's test the second point. This time is f prime of 3 pi over 2. And 3 pi over 2 is going to be on the bottom. So if you would, on your quadrantal, put a dot on the bottom. Label 3 pi over 2. What is my order pair of this one? 0, negative 1. And again, we're still working with cosine. So I need the adjacent movement, which is the x. That number again is what? 0. So we can kind of halfly, we can go ahead and plug this one in, or not plug in, fill it in. At a relative extremum, the derivative is either 0. Can anyone anticipate what the or piece is going to be? Undefined. That is correct. And I'm going to show you that piece on part B. So everyone go to part B on the drawing. So do I have a relative minimum right here? Does everyone see the relative minimum? It is negative to positive, changing direction. What is this called? A sharp turn. Cusp. Can we find the derivative at a cusp? No, it is undefined. So if you want to even use does not exist, you may, but I'm good with undefined. So because it's undefined, I don't even need to prove anything algebraically. All right? So last page, that's going to wrap everybody up. Milo, go ahead and read the instruction on the top.
Graph of the continuous function as was shown on the closed interval.
So it is continuous on a closed interval. So can I use extreme value theorem with the condition given?
Yes.
Yes, we can. Continuous, closed interval, yes, we can. So at this point, let's go ahead and put dots at the extreme points. And for me, that's like wherever it's hanging low or high or at the endpoints. If you want to put more dots, go for it, but it's not going to change the answer. And I think I want to go ahead and put a flat surface on horizontal tangent. Do I see a horizontal tangent right here? Yep. I see one over here. HT as in horizontal tangent. You can write M equals 0. So I count 5 horizontal tangent. Do you? Yes? All right. Let's go ahead and start with the relative minimum and maximum. How many relative maximums do I have here?
2.
The maximum happens where it's going to be changing direction here and here. So someone said 2 is correct. So we have relative maximum is here. And we have a relative maximum. So when the graph is going up and down, that's my relative maximum. So then how many relative minimums do I have?
3.
We got one here, here, and here. So my calculus kids can count. That's a good start, right? You're like, give me more credit. All right, so from here, let's talk about the absolute minimum and maximum. Where's my absolute maximum first? At the very end. Oh, absolute maximum. What about the absolute minimum? The lowest point of the whole thing. The second relative minimum. So they could have 2 different names, which is perfectly fine. So let's answer them. The function has a horizontal tangent, meaning the slope is equal to 0 at the following. When you see the word at, that means what are the x values?
1, 3, 5, 7, 8.
So let's use set notation. So I heard 1. Where else? 3. Where else?
5,
5,
7.
7, and 8. Now we're looking at the function has a relative minimum at. And again, that means we're looking at x values. What x values do we have the relative minimum? Give me the first one.
1,
Second one.
5,
And third one.
8.
And would you guys agree those numbers should be within the horizontal tangent?
Yep.
Yep. And then we have another at for the relative maximum, must be the other 2 we haven't used. What are they?
3,
3 and?
7.
Beautiful. Is everyone good with that one? Okay? So then, the function has an absolute minimum of. So when there's of, that means we want the y value. It's more like me teaching you guys English. So on our minimum, what is the y value of the minimum? -3. What is the x value? 5. And if you want to go ahead and write out the order pair and write out 5 comma -3 and answer that one accordingly, you can. Let's write it as a function. F of 5 is equal to -3.
Like, the y value comes first.
Because y of at x. It's just more of English. I won't trick you like that. Okay? All right. What about the maximum on the absolute piece? What's the y value?
4,
And that's at what x value? 9. So we did graph the slope function back in Unit 1, I believe. We're going to sketch this. So my last class wanted me to sketch it concurrently within the graph. You guys okay with that too? But they kind of want it mirrored right onto it. So here's what I want. I want you to write out something. Write out f of x. And then with a different color highlighter, for me, it's going to be green. I'm going to go ahead and make a bracket for the ending and the beginning of the graph, I guess, right here. And since I am going to use 0, I'm going to highlight that piece as well. Because I used to do this separately, and kids liked it when it was done together. If you have to make it bold on your graph, go for it. Colors would be ideal, though. All right. So we are going to graph. So everything within the green is going to be f prime of x. And the prime means the slope. So let's see where my slope is 0. Isn't my slope 0 right here? Put a dot at y equals 0. My slope is 0 at all the horizontal tangent. And yes, we have done this back a while ago. I think it was still unit 1 though. So at the horizontal tangents, put 0. So watch where my pen goes so you know the direction. Is my slope going up or down right here?
Down.
It is going down, so put a negative sign. All right, watch my pen again. Is my slope going up or down here? Up, put a positive sign. The next piece, my slope is going where?
Down.
Down, put a negative. And then my slope is going up, positive. And it's a little slight down, negative, and positive. Everyone good with that? Xavier, got it? I didn't see you put positive and negative. If only you can look and paste it, right? That would be nice. All right. So then for us to graph the slope function, negative means below the x-axis. Positive means above the x-axis. How high and above, it doesn't really matter. So negative, below, positive, above, negative, below, positive, above, and then below. And how positive, I don't know. I'm just going to end it at that string.